Hello everyone, my name is Reza Tourani. I'm assistant professor at St. Louis University. Today, it's my pleasure to present PERSIA, a puzzle-based interest flooding attack countermeasure. This is a joint work with Misra and George Torres at New Mexico State University. In the past few years, we have been observing a sharp increase in the number of distributed denial of service attacks on the internet. We just compared the number of attacks in the first quarter of 2015 and 2018. We can see that the number of attacks, the frequency increased from about 200 to 1,500 attacks. This is in part due to the infusion of smart devices to the edge of the network, which usually enter the market without proper security onboarded to the network with weak security, and also the popularity of the Memcached services. If you look at the past few DDoS attacks, you can see the footprint of these two events. In particular, the DDoS attack on Dyn and DNS in 2016 was from Mirai Botnet, that is comprised of like 600,000 compromised IoT devices with a peak strength of 1.2 terabit per second. In 2018, GitHub reported an attack with a peak strength of 1.3 terabit per second. And just earlier this year, Amazon reported an attack with a peak strength of 2.3 terabit per second. Now we can see that not only the frequency of the attack is increasing, but also the strength of the attack is on rise. The interesting fact about the 2018 DDoS attack on GitHub was it didn't last more than half an hour, and the reason was GitHub was using Akamai scrubbing service. Scrubbing service is one of the most common DDoS mitigation in IP network. The way it works is the victim requests a service from the provider, from the service provider. The service provider, in the case of GitHub attack, was Akamai. They redirect the traffic from the malicious and legitimate user toward the cloud, toward the scrubbing center they own. And then this happened through DNS or BGP. In the scrubbing center in the cloud, the service basically separated the malicious traffic from the legitimate traffic by linking into the packet attributes and traffic attributes, something like the destination and source IP address and port number, TCP flags, and HTTP traffic characteristics, and then forward the legitimate traffic towards a provider so it can serve the client. Looking at this type of solution, we can easily see that we cannot apply these solutions to NDN networks. One of the major reasons in NDN, we don't have any distinction between malicious packet and legitimate packet. There is no notion of client there. That actually motivated us to look into different distributed denial of service attack in NDN and try to come up with a solution that can resolve the problem. Now, before talking about the solution, let's look at the two types of DDoS attack in NDN. The first, that is called IFA, is interest flooding attack. The goal of attackers is to overwhelm the network resources, in particular, the PET of the intermediate router, through sending volumetric malicious traffic. In contrast to IFA, which is using volumetric malicious traffic, implicit denial of service attack, or IDOS, attackers are basically trying to craft multicast requests with the particular timing and using the features of NDN like request aggregation and loop prevention features to prevent the victim's attack to the requested content. Now, we looked at the existing literature in IFA mitigation, and we noticed that rate limiting is one of the most popular mitigation technique in the literature. The way that rate limiting works is each router individually or collaboratively, they monitor the rate and the statistics of interfaces to detect an attack. When an attack is detected, they basically rate limit that interface. Another interesting solution was self-routing, that is essentially removing the suspicious interest from the PET entry and then add routing features to the name of the packet. We can see the example of this at the bottom of the figure. However, these techniques actually show some shortcoming. In particular, for the case of rate limiting, we noticed that rate limiting can negatively impact the quality of experience of the users that are co-located with malicious user. And again, the reason is in NDN, there is no notion of client inside the request packet. So it's really hard to differentiate which packet is coming from the malicious user or it's coming from the legitimate user. As for self-routing, self-routing actually changed the name of the request as it goes toward the network, which means it undermines caching and request aggregation. Also, it contradicts the NDN's content name immutability. So this actually motivated us to look into IFA problem, and then we actually come up with the idea of PERSIA, which is an ISP-based countermeasure that employs the independent prevention and mitigation mechanism. So PERSIA can be deployed in an ISP at the core and at the edge of the network. At the edge of the network, the prevention phase can be deployed. The essential idea behind the prevention phase is pushing user to use tokens in their communication. And then the idea of the mitigation phase that will be deployed on the core of the network is try to remove the suspicious interest from the P table and store them in other type of structures, in particular in BloomFilter. Now let's look at the prevention phase a little bit more closely. In the prevention phase, the client has to obtain some computational puzzle from the proxies, solve this puzzle, generate a set of tokens, and then use these tokens for communication. In PERSIA, we actually use Lagrangian polynomial interpolation as the computational puzzle. However, I have to say that other type of computational puzzle, something like cuckoo cycle, the hash chain, or even Bitcoin hash cache or Diffie-Hellman puzzle can be used. It's essentially a plug and play feature that can be replaced with any type of computational puzzle. Now, when the user solves this puzzle and generate the solution, they can essentially use that solution to generate a sequence of tokens and use each token only once in their communication. The way it works is the client has to go to a proxy that is deployed by the ISP, request a puzzle, and obtain it either from the proxy or a cache puzzle from the edge router. Having the puzzle in hand, the user needs to solve the puzzle, generate the solution. Each puzzle is also associated with a secret seed that together, hashing the solution and the secret seed together can generate the very first token in the token chain of the client. Having the first token, the user can go through a sequence of hashing operation, hashing the token, the previous token, and the secret seed, and generate a set of K tokens. Now with this token, user is ready to do the communication. However, for the edge router to be able to validate this token, it needs to build the verification table. So the edge router needs to get in touch with the proxy and request a set of information about requested puzzles and its users. So by receiving those information, including the puzzle name, the puzzle solution, the secret seed of the puzzle, the very first token, and the limit of the token that can be associated with that puzzle, the edge router can create this table. Now, having this table, when an edge router receives a request and interest from the user, it simply can verify the token by looking up the token in its table. If the token doesn't exist, the edge router simply rejects the request and drop the communication. However, if the token is available inside the verification table, the router forward the packet or does the cache lookup and then update the verification token. The process of updating verification token is fairly simple. The edge router needs to just generate the next token, which is simply one hash operation, and updating the counter to make sure that the user is not overusing tokens. Now, this actually concludes the prevention phase of PERSIA. However, we noticed that there are some edge router that might not deploy this process. Or if you have a compromised router that does not perform the verification, it actually can forward all the requests, malicious and legitimate, toward the core of the network. And that actually ends up being the major problem in a lot of existing solutions. Now, for that reason, we design a forwarding strategy and mitigation strategy that we call it BloomFilter Assist mitigation strategy, BFA, that the core router can independently run it on their own. Now, this phase actually helps the core router to mitigate the impact of compromised edge routers. The way it works is each core router individually and independently monitor all the interfaces, collect a statistic, in particular the loss rate of that interface. As soon as the loss rate goes beyond a certain threshold, the attack is detected. When the core router detects an attack on a particular interface, it actually detaches the request that arrives from that suspicious interface from the PIT, and then associate a counting Bloom filter to that interface. Using this counting Bloom filter, every time the core router receives an interest from that interface, it adds the name of the request to this counting Bloom filter and then process the interest. By processing the interest, I mean that it can perform an aggregation or forward the packet toward the core of the network. So using individual counting Bloom filter for suspicious interfaces allows PERSIA to do request aggregation, even if you have malicious interest or interest coming from malicious interfaces. So the aggregation can happen either through the PIT, which is the normal NFD operation, or if one of the interfaces that is using counting Bloom filter has the requested content name inside the Bloom filter, then the core router just add the name into the other interface and then aggregate the packet, doesn't forward the request toward the core of the network. This example shows that in the very first step, the router that is connected through the core router on interface 2 sends a request. This request will be forwarded to the core, but when the other router sends the same request over phase 2, the core router look up the counting Bloom filter of phase 2, it sees that that data has been requested before, so it simply add the request name to the counting Bloom filter of interface 1 and aggregate it right there and won't forward it to the core of the network. Now, through this mechanism, whenever a core router receives a data packet, it needs to perform a PIT lookup to answer the request that has been aggregated in the PIT through the interfaces that are performing normally. And then it iterates through all the interfaces, suspicious interfaces that are using counting Bloom filter, and look up the name of the packet in the Bloom filter. If a hit happens, the core router forward the packet through that interface and then remove that packet name from the counting Bloom filter. So to estimate the efficiency and the strength of our proposal, we actually model different types of attackers, including the attackers that are requesting data without solving puzzle or invalid token, attackers that are hijacking user token or performing replay attack, the user that shared their token or their solution or credentials to the other attackers, and then more importantly, the compromised infrastructure that is missing from most of the existing literature. In the paper, we talk about all of these attacks and how does PERSIA solve these attacks. We also talk about two other types of attack: the puzzle complexity and solvability in case that the attacker hired a botnet, and attacks on proxies, the proxy that generate the puzzles. However, in our simulation, we actually group these attacks together. So group 1 include the attackers that they don't use token or use fake token. The second group is about the attackers that share their information with the others, token hijacking and replay attack. And the third group is basically the compromised infrastructure. Now, for our simulation, we actually use 3 rocket fuel topology: Bond, Lestra, and AT&T. And you can see the specification here. As for the edge router, the red number in that row shows the number of compromised edge router that we add to our simulation, which is roughly 25% of all the edge routers in particular topology. We also add 10 provider and 5 proxy to all the topology that we have and made sure that the number of attackers is roughly equal to the number of legitimate users. As for the user, the request rate is selected uniformly at random from the range between 20 to 30 packets per second. Following the ZPF distribution, the client requests data. For the attacker, we actually use CBR attacker, and the rate of the attacker is selected uniformly at random from the range 50 to 100. And we made sure that the attacker are not requesting repetitive data. So each attacker requests individual data and never requests a data twice, just to make sure that there is no aggregation among the attack traffic. So it's actually making sure we have a full-blown attack. We run the simulation for about 2,500 seconds and average the result over 5 runs. One of the problems is we cannot mimic the computational operation in NDN-sim. So actually we benchmark the puzzle solving time and the size, and we infuse it to our simulation. So we selected the puzzle difficulty of 5K, which is the difficulty or the degree of polynomial is 5,000. We benchmark this operation and then apply the corresponding latency whenever the user has to solve the puzzle. One thing that we did is we compared the result of BFA with self-routing and rate limiting. So all of these 3 strategies, they use PERSIA's prevention phase, but when we introduce the malicious routers, they use different type of a strategy. As we can see, the first 500 seconds of the simulation is our baseline, which means we don't have any attacker. 500 to 1000, we have attacker A1 and A2. 1000 to 1500, we introduce attacker A3. And between 1500 and 2000, we introduce all the attacker together for a full-blown attack. And at the end, the last 500 seconds, again, we stop all the attack to see the recovery. As we can see here, this is basically the latency experience of the client. We can see in SR Plus and BFA, the user don't experience any latency degradation even during the attack. However, in RL, the story is different. As soon as we introduce the compromised edge router that let all the malicious traffic into the network, the rate limiting basically stopped dropping the packet from even legitimate user and then cause retransmission, which result in higher latency for the client, so lower quality of experience. And this is also backed with the satisfaction rate that we observed for RL strategy. You can see the satisfaction rate of the client for RL is something between 75% to 80%, 85%. However, SR Plus, which is self-routing, an update of self-routing, and BFA, which is our proposal, they could achieve almost 100% satisfaction rate. The small value of the drop in SR Plus and BFA is just because of the false positive of the Bloom filters. Looking into the throughput measurement of different entities, including users, edge router, and core router, we can see in rate limiting, as soon as we introduce the compromised infrastructure, the expected throughput reduces a bit for all the entities, user, edge router, and core router. This is expected because now we have packet drops and the user have to do retransmission and the network is observing a lot of packet drops. In SR Plus, interestingly, the throughput for the core router increased. And this is an undesired property. The reason is it's not the higher throughput. It essentially means that SR Plus cannot do the request aggregation. It sends all the traffic to the core of the network, even all the legitimate traffic to the core of the network, and then it overwhelms the resources in the network core. However, BFA shows that regardless of the type of attack that we are introducing at different time in our simulation, the throughput measurement of all the entities is always steady, which shows the strengths of BFA and the little impact it might have on the core of the network. We also look into the overhead to back up our hypothesis about SR+. Now here we can see the overhead of the communication among the three strategies. The orange color is showing the overhead of SR, self-routing. The blue line is showing the overhead of rate limiting, and the gray one is the BFA. Something that we can observe is SR+, because of lack of aggregation, is showing the highest communication overhead. And this overhead actually increases with the size of the network. If we compare IBON with AT&T, we can see that the overhead increases dramatically. Following that, we can see that rate limiting has overhead smaller than SR, but is still bigger than BFA. And BFA is always the least overhead on the network, which sort of proves that it can satisfy the quality of experience of the user, but with minimum overhead and minimum pressure on the core of the network. Now we have more results, but to the interest of time, I don't present it here. I will join the meeting after the video and answer all the questions. So just to recap, we proposed PERSIA, which is proposing an edge-centric DDoS prevention mechanism that is deploying at the edge of the network, and a dynamic network mitigation strategy that can be deployed on each core router. So each core router can individually and independently decide to deploy it or not. So the objective of PERSIA was satisfying the expected quality of experience of the user, which through the simulation showed that it can achieve that type of quality of experience, also imposing minimal impact on the network resources, which shows through the simulation, we showed that the communication overhead of PERSIA is much lower than self-routing and rate limiting. Now, as part of our future work, we're actually trying to integrate PERSIA with the token-based access control. And the reason is we're trying to get rid of the proof of work part and allocate the token that are basically reuse the token that are used for the access control as part of DDoS mitigation, which make it more desirable solution. With that, I stop here and we'll join later to take any question you might have. Thank you.